Okay, so welcome back. So in the second, on the second page of your handout, you have some data, and what we're going to do here is we're going to practice extrapolating and interpreting our data. So let's talk about what extrapolate means. When you have data, a lot of times you'll identify patterns and trends. And in our case, the pattern and trend is such that for the half-life, we divide the amount by 2. And then on the time, in the time column, what we do is we can add or subtract the amount of half-lives there. So by following that trend, dividing our amounts by 2 or subtracting, adding the half-life to the time column, we can extend this table beyond where it currently is. And that's what we do when we extrapolate. We're kind of extending our data using the trends that are there. All right, so we're going to extrapolate the data to do the first one for number 4. So this is actinium 222, and we already determined prior that actinium has a half-life. So if you go back to this previous question, it has a half-life of 5 seconds. I'm just going to write that above, so we'll just keep track of that. Okay, and that's just something to keep in mind when we're extrapolating. All right, so it says predict how much actinium remains after 25 seconds. Now our table right now ends at 20 seconds, but I need it to go to 25 seconds. Now since each half-life is 5 seconds, that would be one more half-life. So in the time column, I'm going to add 5 seconds, that's one half-life, to go to 25, okay? Now, when I do that, remember, each half-life results in the radioactive isotope decaying by half. So what I need to do to the amount of radioactive isotope here is divide it by 2. So I'm going to divide that by 2. And so to go from, so I take 100 divided by 2, and that gives me 50 atoms. Let me go ahead and zoom in here. So on the time side, I just added 5 seconds. And that corresponds to one more half-life passing. And so then on the amount side, I had to divide it by 2 since that was one half-life. All right, so that means that in 25 seconds, I'm going to have 50 atoms. I've extrapolated my data. Now in 35 seconds, all right, let's see about that. Well, remember the half-life is 5 seconds, so should my next value here be 35? That's right, it can't be 35. I have to add 5 at a time because each half-life is 5. So I'm going to go from 25 to 30, and then from 30 to 35. Okay, so that means essentially 2 more half-lives have passed from my last position of 50 atoms. So once again, I'm going to have to divide by 2. 50 divided by 2 gives me 25, and then I'll do it one more time, divide my amount by 2, and that will give me 12.5, okay? All right, so I have 12.5 atoms. Now I'm going to go ahead and write that down, but we're going to see why that is not the best answer here. Because my amount is given in atoms, you can't have a half of an atom. Now you could have a half of a gram, so if these amounts were given in grams or in percentages, you could have a half a percent, but you can't have a half of an atom. So what we're going to do, instead of writing 12.5, we're going to use this squiggly line as an approximate, and we can say it's approximately 12 atoms that we have, or we can say it's approximately 13 atoms. But remember, we can't have 12.5. We can't have a half of an atom, all right? So let's just recap what we did here. We extrapolated our data for these problems, which means to extend out our data using our understanding of how the data changes over time. And so for 25 seconds, that was one additional half-life. So we took our amount, 100 atoms, and divided by 2 to get 50 atoms. And then for 35 seconds, that was 2 more half-lives from 25. And so we had to divide by 2 twice. So 50 divided by 2 gives me 25, and 25 divided by 2 gives me 12.5. And then because our units are in atoms, we had to change it from 12.5 atoms to 12 atoms or 13 atoms because we can't have a half of atoms. Of course, if this was grams or percent, we could leave it at 12.5. Okay, let's look at our next example. So now we're looking at the daughter. Remember, in a radioactive decay from the Candium lab, for example, you start with your parent and then it decays into your daughter. In this case, our parent is actinium-222. This is sort of like our candy. So our candium. And the radium-222 will be like our greenium. Those are the P's, right? Now, every time an actinium decays, it makes one radium. So what we need to do is here, we're kind of keeping track of the amount of radium that is produced from the amount of actinium that decays. So let's start off at 0 seconds. Like that's our initial time. Well, initially, would we have any daughter isotope? Think back to when you did the Candium lab. When you started, did you have any greeniums? Did you have any split P's in your mixture? No, you didn't. So at 0 seconds, you're going to have no daughter isotopes. All right, what about at 5 seconds? Well, at 5 seconds, we went from 1,600 atoms of actinium to 800 atoms of actinium. That means that how many atoms of actinium decayed? 800. So 800 atoms of actinium decayed. Well, the amount of actinium that decayed corresponds to the amount of radium that forms. So these will be the same amounts, just like with the greeniums and the candiums. You would replace the decayed candiums with greeniums. Let's take a look at 15 seconds. So here we are at 15 seconds. So at 15 seconds, we went from 1,600 to 200, okay? So 1,600 minus 200. That means a total of 1,400 actiniums decayed, right? Because we had 1,500 and all we have is 200 left. So that would be the amount of radium that we have here. All right, last but not least, for 25 seconds. So again, we start off at 1,600 atoms, and at 25 seconds, we have 50 atoms of actinium. That means we had 1,550 atoms of actinium decayed, and that would equal to 1,550 atoms of radium. So the idea here is that the number of actinium that decays equals the number of radium that forms. And then remember, the actinium is our parent, and the radium is our daughter. So the parent produces the daughter. Okay. We're going to take a look at one last table together. So in the last table that we're going to look at, we are given molybdenum, and once again we actually already determined the half-life for this molybdenum. We determined the half-life in the previous part to be 4,000 years. So I'm just going to write that here because that's important for us to know. Alright, so it asks us here, how much molybdenum-93 will the rock contain in 8,000 years? So we have a rock that has this molybdenum in it, and as the molybdenum decays, we're going to have less and less of it in the rock. But once again, our table doesn't go to 8,000 years. It stops at 4,000. So we're going to have to extrapolate the data, extend this table out a bit. Okay, so let's go ahead and do that. Now, each half-life is 4,000 years. So to go from 4,000 to 8,000, that's just adding on one more half-life. So we're just adding on 4,000 years. And so since we're only adding on one half-life here, we're going to take the amount we currently have, which is 50%, and divide it by 2, and that will give us 25. So it's 25%. And that's how much molybdenum the rock will contain. And to explain our answer, that's because from 4,000 to 8,000 years, is 1 half-life, so we're going to symbol half-life as T half. So the answer is half of 50%. Okay. All right, let's try the next one. If a rock contains 70%, 70.7% molybdenum, how old is the rock? Explain your answer. All right, so we're going to, in this case, we're not going to extrapolate. We're going to interpret the data as that's here. So what I'm looking for is I'm looking for 70.7% molybdenum. And again, this is in my amount column, so I'm going to look in the Y column, and I find my 70.7% here. And if I go over to the X column, my time, that's 2,000 years old. That's how old the rock is. And that's because that is the time that corresponds to 70.7% of molybdenum remaining. Okay, there we go. All right, now let's look at our last one. For our last one here, it said if the rock contains 12.5% molybdenum, how old is the rock? Explain your answer. So once again, we're going to look to see if we have this information in the table like we had it in the previous one. So let's say we see 12.5% in our table. I look in my table, and in terms of amounts, I don't see 12.5%. So what do I need to do? I need to extrapolate it. All right, so to extrapolate it, I'm at 25% right now, right? Because that's what I extrapolated to last time. I need to go one more. So to go from 25 to 12.5, I need to divide it by 2. And that will be an additional half-life. So what's going to happen to in my time column? Am I going to double this time? What am I going to do with this time? Remember, each half-life is 4,000 years. And in the time column, you're just adding time. You're not multiplying or dividing over here. So I'm going to add 4,000. 8,000 plus 4,000 gives me 12,000. So that means that the rock would be 12,000 years old. And that's because one half-life has passed. So one more half-life. Since 8,000 years. And each half-life is 4,000 years. Okay. So a couple of things to sort of keep track here. When you're dealing with extrapolating or interpreting the data, you want to remember that in the time column, your X column, you're just going to add and subtract depending on the direction that you're going. If you're going down the column, you're going to add your half-life time. You do not multiply or divide here. And then for the amount, you're going to divide if you're going down. If you're going up, of course, you would multiply by 2. You're just dividing by 2 here. So in the time column, you add or subtract your half-life. In the amount column, you multiply or divide by 2. So make sure you're keeping track of that. All right, take a moment to write a summary of what you have just learned. It's a lot of information here, a lot of good scientific extrapolating and interpreting. If you have any questions, please let me know. Have a quality day.